Hello, everyone, and welcome to the webinar on accelerating your Spectrum Scale or GPFS environment. My name is Keith Parker. I'm the Director of Product Marketing here at Pavilion, and I'm joined by Keith Ober, our Senior Principal Architect. In this webinar, we're going to talk about a number of different things, including the impact of the legacy storage architecture on parallel file systems and ways you can go ahead and improve that performance, sometimes significantly. We'll talk about the differences between NVMe and NVMeoF and why that matters to your environment, because everyone's very familiar with NVMe as a drive interface, but NVMeoF, well, not as widely adopted as of yet, is poised to actually have the bigger impact. And we'll talk about how you can dramatically improve the performance of your Spectrum Scale storage, while at the same time reducing your hardware footprint, simplifying your architecture, reducing your costs, and perhaps most importantly, getting compute cycles back that you can then apply to your application. Because at the end of the day, that's what you want your compute cycles doing, running your applications, not managing your storage. And with that, I'd like to introduce Keith Ober to go ahead and talk about why file systems matter.
Thank you, Keith. Always a pleasure to join you. So I'd like to start with just a quick refresh on kind of the building block of the architecture. And, I think of it as a bit of a pyramid. And, if we think about where the market is today with object storage capabilities, my mind often goes to the cloud providers, the Amazons, the Microsoft, the Google architectures. And these architectures hold massive amounts of data, but that architecture is fundamentally more of a latency-driven architecture, and you're typically talking about gigabytes per second, kind of on the upper end of that design. And that's not really the fastest architecture that you can have. But as you get into more performant workloads, you'll find scale-out network-attached storage. Typically your NFS type workloads are often very common. And these architectures continue to drive down latency and drive up performance. And I've worked for a number of different technology companies in the past, and gigabytes, tens of gigabytes are even possible these days with the most recent architectures in this design. But if you're really looking at a high performance architecture and you've got demanding workloads, this is where you creep into the parallel file systems. This is very common in some of the high performance computing centers. I find this in research. In mission critical applications where you need to drive not just tens of gigabytes, but you need to drive into hundreds of gigabytes per second. And these architectures really have the ability to drive single client IOs. It's network optimized for things like InfiniBand. And that's really where you see the highest performance, top of the pyramid type level performance in these architectures. So if I go back and, talking about the higher performing workloads, a lot of times people take NFS and the NFS architecture and they want to push it into the next level. But, ultimately you're hindered by the overall design of NFS. And even the scale out architectures, kind of the devil's in the details. They'll talk about these really high tens of gigabytes per second of throughput. But what the fundamental architecture actually is limited a lot of times between a single server and a single node in even these scale out architectures. And it's really a function of how NFS operates. So it establishes a single connection. So if your server's connected, even though there's multiple nodes on the storage side, you're only connecting to potentially one of those storage nodes or maybe one of those blades in that design. Take a look now at how GPFS works and how this is really how these parallel file systems really differentiate and drive that higher performance. With this type of architecture, you can see a single server makes multiple requests into the storage subsystems. And this is how on a single system, I've seen 10 gigabytes or even better than that to a single server in a GPFS architecture. And that's really how you drive up individual client performance. And then across even a small set, tens and more of nodes, you might see hundreds of gigabytes per second possible, even in relatively small compute farm of systems. It's really around how GPFS works and how it's optimized.
I totally agree, Keith, and I think that's one of the most important things for people to take away from this is it's not just a matter of the total overall performance that a storage solution can provide, but it's what kind of performance can that storage solution provide to each individual node accessing it? What's the individual client performance, not the overall aggregate performance?
Well, you're absolutely right. And, in these higher performance computing environments, they also take advantage of the latest in network throughput. And oftentimes they're talking InfiniBand. Even to the end servers, these InfiniBand connections are often 100 gigabit Ethernet connections or 100 gigabit equivalent for InfiniBand, like EDR. And this year, the trend I'm seeing is anybody buying compute side, everybody's looking at HDR and potentially HDR 100 to the individual servers. So again, it's demand to drive high throughput capabilities, but that same architecture drives low latency between the storage and the server.
Exactly right.
So if I step back, I think, Keith, it'd probably be helpful to describe kind of what I see in the market. So, IBM Spectrum Scale, it's been around for a long time. It's more commonly referred to in the industry as GPFS. But, some folks think that it's really, this older architecture. But what you may not realize, they've been continuing to innovate in this space. With their architecture, they've made inroads with tiering and capability to plug into a myriad of different use cases. I see it coming up with AI and facial recognition platforms where there's a need for high-speed ingest. Well, a parallel file system is really designed to do high-speed reads and it's capable of high-speed writes as well. And that's very different from what you find in a lot of these other HPC environments. They have the ability to plug into things like gateway appliances, and this has allowed GPFS to really kind of come back into the media and entertainment space. There's a couple of these industries that continually bump up against the limits. Media and entertainment, as they're making the transition from 4K movies to 8K movies. We've been working with some of the movie studios on being able to deliver next generation performance for rendering and those types of workloads. I worked at National Cancer Institute for a long time in the genomics space. And one of the challenges I was always faced with was, here's the goal for the next 6 months, but I also had to be able to anticipate what was coming a year from now. In genomics, the sequencers would change quite frequently. I go from a Roche 454 sequencer to a Illumina sequencer that doubled or tripled the amount of data that could be generated. I always had to be on my toes and willing to make adjustments to support the growth that was happening in the industry. Spectrum Scale is one of those technologies that allows people to future-proof their designs and anticipate, they have the capability to drive the top of the pyramid performance for all of these kind of really edge-of-the-envelope use cases.
And that's so true because the spectrum scale use case applies across so many different industries and so many different applications. There's really no area that this type of solution doesn't touch.
Yeah, it's hard to put it in a box. There is a definitely 2020 has been an interesting year for folks that unexpected events meant new workloads, new dynamics for the architecture. And so, we see this continually coming up in customer use cases where they have designs where they want to create the next roadmap so they have a vision for the future.
Exactly. So with that, let's go ahead and talk a little bit about what some of the challenges are with this type of environment. One of the challenges that we've seen has really been that people assume the storage media is the limiting factor as we've moved from hard drives to SSDs to mixed environments. And really, it's no longer the media itself that's going to be your primary bottleneck. It's actually going to be the overall architecture of the array controller. I've been doing storage far longer than I care to think about. And I remember being an old SCSI guy dealing with ultra-wide SCSI arrays way back when. And these were arrays that had a few hard drives in them. They were connected they were directly attached. And if you looked at the array, that architecture that was used in that array, it would actually look exactly the same as the architecture of the latest all-flash array from pretty much any primary vendor out there. It's going to be based upon a dual controller design. Now, a lot has changed inside. We've gone from the SCSI interface for the drives to a serial attached SCSI SAS interface, all the way up to what's now NVMe. And NVMe really came into its own as the drive interface of choice, because what it did is it really enabled flash media, which had been put on SAS for very good reasons. It really enabled that flash media to deliver the kind of performance that that medium is capable of. But then when you get into the actual array itself, well, the array is still based upon a dual controller design, exactly like it was, 25 years ago when I was first dealing with these things. And so that hasn't changed, and that's really been the limiting factor, is that single or dual controller design of those arrays. Now, when you look at that design, what you're going to see is that, you've got, your controller. It's got all the data is going through a single processor or maybe a dual processor, depending on how it's set up via either active-active or active-passive. And all the data has to flow through that processor. And what's that going to do? That's going to limit the amount of throughput you can get, because you're limited by the processor on that individual controller. You're limited in terms of performance because that processor is going to get saturated by only a few SSDs. You're going to have single points of failure. You're going to have issues with backward compatibility, which is going to limit your performance, because that legacy design is going to include a lot of stuff that you just don't need today. And that's why the Pavilion HFA took, our hyperparallel flash array took a fundamentally different approach. When we went to design our array, we went back and we looked at it and said, this just isn't working. So we went into the data center. What's the fastest thing in the data center? Well, that's going to be your network switch. So when we looked at it, we said this network switch is the only thing that can transfer, terabits per second. So we designed our array around that type of fabric. It's a high-speed, non-blocking switching fabric capable of 6.4 terabits per second of throughput. And what that has enabled us to do is to move from that legacy dual controller to up to 20 storage controllers in each individual array. What does that do for us? Well, it gives us flexibility. We can have multiple networking ports, multiple storage controllers, all accessing data at the same time, providing greater aggregate throughput. We have unbelievable high performance, 120 gigabytes per second of throughput from an individual 4U array. Because of the switching fabric, there's no single points of failure. And it's designed for NVMe from end to end with no need to have support for any kind of legacy technology. And what this has really done is enabled us to provide the hyperparallel flash array, which is a true game changer for GPFS and parallel file systems.
Well, you're spot on. That's really a building block for going to the next level. If you think about it, being able to go with, like you said, the NVMe drives, kind of been in the industry for a while as well. 64,000 queues, that's great per drive. But if you're going to extend that out, you're not going to stop at the individual box. And this is where you're going with this, is you're driving this ultimately out to a client.
That's exactly right. And that move to NVMe really freed up so much of what the SSDs could do. You talk a little bit about the queues. When SSDs were attached through SAS, or even worse through SATA, they were limited to a single queue. And that queue depth was limited to 64 outstanding requests, or less if it was SATA. With NVMe, each individual drive was able to support not one queue, but 64,000 queues. And each of those 64,000 queues has a queue depth of 64,000 commands. So what that really does is that unleashes the ability of that flash media to provide not serial, but parallel data access, really unleashing what these drives can do. And what NVMeoF did is it took that NVMe advantage and extended it not just within the array, but across the entire fabric. So it's a single connect end to end from storage to host. And that took away a lot of the things that were really holding it back, let's say storage networking back. So you're no longer limited by the drive interface. You're no longer limited by the SAN interconnect. So you're not limited by those ports. You can now use high-speed networking to truly get the kind of performance these solutions can offer. So what's really driving the need for this kind of performance? Well, when we look at the data center, we've seen a significant evolution really everywhere. You look at the scale-out infrastructure. So whereas people used to, build everything based on a virtualized environment, be it, VMware or Hyper-V or Zen Server or whatever their hypervisor of choice was, they're moving more to scale-out applications with Docker and Kubernetes. And even if you're running VMware vSphere 7, which now supports Kubernetes, you might have some type of mixed environment. It's really around providing that scale-out infrastructure that allows you to expand your data center and provide resources on an as-needed basis. And the thing that's driving that are the scale-out applications. It could be some type of big data solution, such as Hadoop. It could be, Apache Spark. You could be doing something with AI and Elasticsearch. Maybe you've got in-memory databases like Greenplum or MongoDB. Whatever it might be, these applications require scale-out infrastructure to really enable them to deliver the type of solutions, the type of information that these applications can offer. And what is it that they truly require? They require consistent, predictable, scalable, high performance storage that also delivers ultra low latency. It doesn't do good to have consistent performance if it doesn't scale. It doesn't do good to have predictable performance if it's low performance. It needs all of these facets to truly deliver on what these applications can offer. So what we've seen is scale-out infrastructure has moved to a parallel infrastructure, and scale-out applications are now operating in parallel. And tying into that, servers are now doing the same. So whereas it used to be you could scale them out, now with these parallel file systems, they're providing parallel access to that storage. So if everything else in the data center has moved to a parallel infrastructure, shouldn't the storage do the same thing? And that's what the Pavilion Hyperparallel Flash Array does, is it moves from dual controllers to multiple controllers. It moves from limited, old SAN interfaces to high bandwidth IP or InfiniBand ports. It supports modern protocols, NVMe and NVMeoF. Well, we're not limited to those. We can still do, legacy protocols if necessary, such as NFS or iSCSI. But the key facet is we support the modern protocols for maximum performance. And we support that across different data types, block, file, and object, with extreme high performance and ultra low latency, while supporting the ability to start small and grow that environment on an as-needed basis that scales both linearly and independently. You can scale performance, you can scale capacity, you can scale both, you can do it as needed, and the result is that you actually get all the performance of DAS and all the benefits of shared.
That's great, Keith. When you stop and look at the architecture, this is a back view of what a Pavilion chassis looks like. You're probably thinking this looks a lot more like a switch than it does a storage device. And that's really goes into what you were just saying about how the architecture drives that parallelism from the drives all the way out to the clients. So in a very small 4 RU, 4 rack unit space, we have the ability to have 20 active controllers. We have the standard redundant management cards built into the design, so you get the high availability. And then on the networking side, we have 40 Ethernet or InfiniBand ports. A fun story here is we're a company that's continuing to innovate. So When we first started out, we were an Ethernet-based architecture. One of our customers came to us and said, you know what would be really interesting is if you could architect this system to also support my EDR InfiniBand architecture. Guess what? Our engineering team went back in a very short amount of time, created and integrated InfiniBand into this design so that from within the web interface, you can flip the switch at a software layer to say whether you want this port to be InfiniBand or Ethernet. And this is really kind of what helped drive this architecture to have ultimate flexibility when it comes to delivering the lowest latency possible, whether it's even Ethernet based or whether it's InfiniBand based. And I love the innovation because that's kind of what drives me as well. Power wise, you know, it's a simple 2+2 power architecture. So again, it's all about simplicity and design and the ability to deliver this to an end customer very simply and very easily with the maximum amount of performance to the end client.
And speaking of performance to end client, that's actually the next thing I'd like to go ahead and talk about is the way we're able to deliver predictable, consistent, scalable, high performance for block, file, and object. And that's one of the key things I want to go ahead and highlight here is that we're able to provide extreme high performance for all three types of data. When you look at a typical dual controller array that supports multi-protocol or unified storage or whatever they want to call it, what those arrays typically do is you'll have your storage and it's really architected around providing one particular type of data. We'll use file as an example. It could be block, could be object, doesn't matter, but we'll go ahead and use file for the purposes of this discussion. And that array is going to be really, really good at supporting file level data. And then when it adds support for object, what that vendor is doing is they're taking their file data and they're running object on top of it. So the controller and the software is responsible for managing the conversion of object and file. The result is it's still going to be really, really good for file, but object, not so much. The performance is just not going to be there. And that's true regardless of whatever the base protocol is and whatever the protocol put on top of it is. So this is true pretty much across most of the storage vendors that support multi-protocol. And that's because they have a dual controller architecture and they're limited by the number of controllers.
That's a great point, Keith. And if you think about it, with our architecture, we've built the groundwork under the covers to drive all that parallelism. And if you think about it, if you've designed the architecture right, it shouldn't really matter what type of protocol you're actually leveraging on top of that. If you've built it correctly, you'll have something that's going to be performant for each one of these workloads. And that's really what you see here. I mean, if you look at it, the capability to do 120 gigabytes of read on the block level, the ability to do 90 gigabytes per second for the file level, and object close to the same number, 80 gigabytes per second, all of them delivering massive amounts of capability. Now, what's even more interesting is that because we've architected it with all this performance and all this parallelism, you don't get the degradation that everybody else gets. Everybody else gets this huge delta between their reads and their writes. When you look at the difference between ours, it's very marginal as far as the performance difference. Obviously, there is some overhead in that, but we're much faster on the write capability versus the read than what everybody else is. And again, it's the parallelism that we built into the design allows us to deliver unprecedented amount of read and write performance.
That's exactly right, Keith. And when you look at what we're able to do and how it compares to the competition, there's a number of important things to look at here. So there's the performance, absolutely. 120 gigabytes of performance, 90 gigabytes of performance, 80 gigabytes of performance. Something that's people didn't really think was attainable with a single array. But it's also the IOPS, it's the latency, it's all of those combined. When you look at the our write latency for block, 25 microseconds, and what I want to highlight is when we talk about 25 microseconds of latency, we're talking about across the fabric. Typically, when you've got an all-flash array vendor and they talk about their latency, what they're really talking about is the latency of the array. So from the time the array receives the request to the time the array puts the response back out on the wire. So it's everything that happens internal to the array. That's not what we're talking about. Because we use, RDMA, and we have the ability to place data from storage directly into the system memory of the host that's requesting the data. We're talking about the time the array receives the request until that request is fulfilled at the node that made the request. So across the entire fabric.
That's really a very important point, because it's the full loop of that request, right? And I often think of this as, read the fine print as well, because these numbers kind of stand on their own. But what I find is when I look at what others will tout, they'll talk to, hey, I can do something close to this performance number. People will say I can do 15 million IOPS, and this might be a leading storage company out there or part of an even larger company. But the devil's in the details, right? When you start to unpack that, you look at how do they deliver 15 million IOPS? Oh, wait, it's 80 rack units of space. So that's multiple racks of gear stacked together in order to deliver what we can do in a very small 4 rack unit space. Not even a quarter of a rack. We're delivering more IOPS than 2 full racks of gear. 80 rack units of gear to deliver even less than what we can do in a single appliance. That's pretty phenomenal.
Yes, that's absolutely one of the key things is when we talk about performance density, and you're absolutely right. And when you look at that across the board, it holds true. When you're looking at file, somebody might have 15 gigabytes per second of read, so a small fraction of what we're able to do. They do it in the same space, but it's a small fraction of the performance. So is it performance? Is it capacity? Is it density? The one I particularly like to hone in on is object. When you look at local object, there's one vendor out there that touts the fact that they have the fastest object storage in the world at 171 gigabytes per second of write performance. Well, that's true. They were able to achieve that, but do you know what it took them to do it? 704 rack units of servers to go ahead and do it. That is a staggering number. It essentially took an entire data center to achieve that. And we're able to achieve high performance in a single 4U appliance. We're able to achieve, because we scale linearly, we're able to meet and match that in less than a rack. So it's not just
say, this is a really interesting space, because a lot of people, we're talking to folks that are dealing with high performance computing. But if you think about it, I've talked to people who said, if I could write everything in object today, if all of my applications supported it and my workflow supported it, I would go to this. But when they're thinking about it, they need something that's going to be fast. And this is kind of forward leaning. I think the capability to do high speed object with low latency is the future of a lot of these workflows. It may not be, like I said, the point on that pyramid for as far as peak performance, but what if you could get something that could do hundreds of gigabytes per second with object at the, that replaces potentially your NFS stack, your middle of the road performance level with object. That's kind of game changing in my opinion for future workflows that people are looking at.
I agree. And the thing about it is, it will give you best of breed performance for your applications today. And as those applications migrate from NFS or block or whatever they happen to be to object, it'll give you best of breed performance tomorrow in the same platform.
Absolutely. That's great.
And it's not just that performance, it's density. And sometimes people will overlook this, but you just can't overlook how significant the impact of performance density is. We had a real world scenario where a customer was looking at a solution, and they had architected something from a leading vendor that would give them the performance they needed, but it took 2 full racks of storage and networking to do that. We were able to come in, exceed those performance numbers in a single 4-rack unit appliance. The fact that we can consolidate racks of capacity down to 4-rack units and still improve performance, improve latency, improve density is it's just astounding.
Well, it's really game changing. I mean, I worked in data centers longer than I care to admit. And I'll be honest with you, Keith, I never had enough rack space, and I was always looking for ways to consolidate and shrink my footprint. The fact that we can deliver higher performance in a smaller footprint with more capacity is just, it's awesome.
And the other thing I really think we need to highlight is cost. When you're looking at going from 2 racks of equipment to a single solution, what are you saving in terms of not just the obvious floor space and power and cooling, all that, but what are you saving in terms of per port costs on those switches? If you're looking at fiber channel interconnects with that many per ports on your fiber channel switches, and you're able to move to not just a smaller solution, but a more affordable interface, a storage array that's effectively going to be the same cost, the savings are astounding. So that single array is able to deliver over a petabyte of usable capacity, 20 million IOPS, 120 gigabytes per second of bandwidth, and as little as 25 microseconds of latency across the fabric, which is on par with a direct attach NVMe drive, all in a 4U chassis.
So getting back to kind of the IBM Spectrum Scale design, we started out working with IBM and customers where they have the traditional design where they got, at the top of the image, you can kind of see all the server architecture that's out there. This could be tens of servers to hundreds of servers, thousands of servers, depending on the design. And a lot of customers have gone with NSD servers to abstract out the management of this design. And we can come in with Pavilion, and we could provide the storage pools to those NSD servers. And that way, we can NVMe map that storage into those NSD servers. But, some of the challenges that we run into in this space are people that need to drive down latency. And working with IBM and others, there are better ways to solve this for a number of use cases. So if we go to the next slide, you'll see this is really a way to, you talked about early on about IBM being around for a long time. Well, what if you could really breathe new life back into the IBM design, the IBM Spectrum Scale GPFS environment? What we did is we were able to take our volumes spread across multiple of our systems and map those directly into the compute infrastructure. And this solves some really big challenges. Number one, it simplified the overall architecture. You don't need a layer of NSD servers in there to manage it. Number two, by eliminating the NSD servers, you've actually reduced the cost of the overall solution because now you've got the volumes mapped directly into IBM compute nodes, and you've removing those servers. Now you can spend more on the compute stack, more money on buying additional GPUs, maybe to put in those servers. Again, it saves you cost for the number of servers you have in that design. And then thirdly, if you think about it, now you're bringing in each one of these systems. In this example could be a petabyte of usable capacity. So with 3 of our systems mapped in, that's 3 petabytes of usable space in, again, less than half a rack, a quarter of a rack of gear. 3 petabytes that could deliver, I don't know, 230 gigabytes per second of write, 250 gigabytes of read to your IBM Spectrum Scale environment. This is really game changing for folks that have mission critical applications Even folks, IBM Spectrum Scale has hooks into things like Hadoop and other things. So this could be an ideal workflow for big data projects. Again, giving you the flexibility to drive hundreds of gigabytes per second in and out of the IBM Spectrum Scale environment, reducing cost, simplifying the design, and oh, by the way, IOPS. IOPS are kind of the hidden piece of this design because in a traditional environment, you've got to wait for IOPS to be delivered. Each one of these Pavilion systems is capable of 20 million IOPS. So you add them together, you've got 60 million IOPS that are possible from the Pavilion chassis under the covers. That gives you tremendous capabilities for your IBM Spectrum Scale environment.
That's exactly right, Keith. I mean, the things, the opportunities this opens up to people is just game changing.
And if you think about it, what IBM's use cases are, that they're, folks with GPFS environments, they're really looking now, this day and age, they're looking at integrating into these environments AI analysis of facial recognition. It's the autonomous driving. It's the ability to do sensor ingest, where you want to process in near real time certain workflows. Cybersecurity, you name the use case, and AI is being applied to that use case today. You think about the life sciences, the amount of research that's capable if you take advantage of combining some of these. You combine AI with genomic or life science research or drug discovery. You combine AI with media and entertainment, and now you have the ability to auto-detect and track pieces within an image. All of this is kind of coming together, and what you really need are really strong building blocks to go and tackle these really big, tough challenges. And I believe that a combination of IBM Spectrum Scale with Pavilion is one of those building blocks for people really driving the next generation of applications and use cases.
I think you're absolutely right, Keith. And as we move into the really the next generation of these applications and these solutions that are, well, let's just say never been more critical to the world today, the ability to move more data, to process more data, to apply more compute cycles to your applications than simply managing your storage, this is truly going to help drive the next generation. And with that, I'd like to thank you for attending this webinar on accelerating your GPFS environments. If you do have any questions or would like more information, please visit us at pavilion.io. Thank you.
Good job, Keith.